Good morning, good afternoon, good evening. Welcome, everybody. Thanks for joining us today as we talk about how to tackle software testing and regulatory compliance for IEC 61508. My name is Arthur Hicken, and I'm your host, and will be co-presenting. With me today is my colleague, Ricardo Camacho. How you doing, Ricardo?
Doing very well. Hi, everybody.
So we've got some interesting content here worked up. I know this may seem like it's a dry topic, and we're going to try and make it a little fun for you today. So hopefully you'll enjoy it. There are question boxes at the right. If you want to ask a question, get it in over there, and we'll try to handle it at the appropriate time. Slides, video, etc., will be available afterward. You'll get an email letting you know how to watch it and share it with your friends if they couldn't make it. So today we'll be covering how, software is in everything, right? The robot revolution is upon us. And everything that you look at is somehow connected somewhere, doing something on its own, making its own decisions. We'll take a glance at the standard itself and try to explain how you can apply the standard to your process in a very practical way. And then we'll take questions and answers at the end. So as I mentioned, internet connected things are everywhere, and we see this in industrial automation. We see it in smart health today. We see it in smart cities. Years ago, Cisco projected over 50 billion connected things would be available. I'm starting to feel like that number is extremely conservative. That number might be 2 or 3 or 5 times that big when I start to look at things like Apple AirTags and smartwatches and smartphones and multiple devices in cars. It's unbelievable when you think about industrial automation relying on a network, not just of big devices to do some work, but sensors and actuators. The number really explodes. And the trick is that as we take these devices and robots, et cetera, that were working for us, and we start to add code and connectivity, it gives us a lot of opportunity to solve problems we couldn't solve before, to do things faster, cheaper, easier, more repeatable, safer. But it also brings risk, and it brings risk in a couple of different ways. And one is the human and industrial interface, which we'll talk about in a moment. And another is just the rising cyber threats that are occurring. And you can see this in the news every day. There's a variety of things ranging from data breaches to device failures and various kinds of problems that occur in a very regular basis. And again, these devices, it becomes more important because they've permeated our life, right? Anywhere from inside of factories that are delivering power to our homes, on ships, on airplanes, the robots that are building the cars that we drive, the robots that are packaging and shipping the packages that we all order on a daily basis online, voting machines, traffic signs, right? Not just traffic lights, but actually the warning signs that we're used to. So these things are just everywhere, right? And again, they bring all this opportunity, but they also bring all this risk. And in fact, everything that you see on the screen has been breached in one way or another at one time or another. They're all actual devices from actual security breaches. The other thing that we have to think about, of course, is safety. And I'd argue about security, but safety first. If the device isn't safe, then who cares if it's secure, right? It should be turned off. When we think about safety, the first step is it's safe when you use it properly, right? So if the person's doing the right thing, the thing that the device was built for in the right way, that the device shouldn't cause harm to them. From there, we also have to think about, well, what happens when it fails, right? And some of these devices, we put them in factories and they're under more extreme conditions and they're under long-term conditions. The lifespan can be quite extensive. And eventually things will fail. Parts will wear out, power will get tripped over, other things will happen, weather happens. So it's important that when devices fail, that bad things cannot happen. And it's something that you have to think about. But another use case is also improper usage, right? There's an old adage that to a man who has a hammer, everything looks like a nail. And that's a if you were building screws, that is a use case that you have to expect is going to occur from time to time and plan out how you're going to respond to it. It's the same with every other device we get. Go to YouTube and Google fail, and you'll find people using devices in a crazy variety of ways that were unexpected, but you still have to think about. And then, of course, when they're under attack, right? A screw might hold something together and keep it safe, but a man with a screwdriver can alter that scenario. And so you have to think about it again. How reasonable is it? How frequent? What do I need to do to protect against it, or to make sure that in that mode that bad things don't happen to the consumer? As I mentioned, I want to talk about the human robot interface. ADAS is fascinating. Ricardo and I talk about it all the time, just, like quote unquote for fun, right? Like as part of our normal lives. But it's a really interesting, challenging problem. If you take a car and you drop it on a Hollywood backlot with modern software from multiple vendors today, it'll do a pretty good job getting itself around. You might even be shocked at how well it can park, navigate, route, etc. But boy, you turn humans loose and suddenly it's a mess. And I'm not even talking about other cars, but just humans on foot. Pay attention when you're driving around next time you get in your car, like what weird stuff people do. Are they entering the street? Are they looking at the street? Do they jump out in the street? Do they open a door in front of you? Do they pull out their car in front of you? It's really, really shocking because people do very unpredictable, atypical things on a pretty constant basis. And so one of the biggest challenges that is still facing us in automated driving is the fact that we have to interface with humans. And we see the same thing in other areas. We're moving to a much more frequent drone delivery um, model where people are using drones, whether it's a flying drone, a little driving drone. I know we have people that work here at Parasoft whose kids are involved in various programs where they're delivering drones. They do deliver to dorm rooms and things like that. And again, you have this problem because if the drone is small and light, someone can pick it up and steal it. If it's flying, it can crash into someone's face. So you have to think about, again, all these various scenarios. And then the factory robots one, right? And I just love this old Lucy one because, this is a early factory human robot interface. The robot here is merely the conveyor belt, but it's moving at a speed that the human can't handle, and it ultimately causes problems. We have earlier on, my picture showed the classic arm that we use in assembly, like aircraft and automotive, etc. And those are nice from a safety perspective in the sense that we can easily demarcate exactly where they're going to reach and where they can't reach. But now we have these more modern ones loose in factories, especially in shipping, for example, where they drive around and interface where the humans are. And so it's very important, again, to be able to understand, will I encounter a human? How will I respond when I encounter a human? And things like that, so that people don't become injured. So it's a very important part. Now, the interesting thing that's happened over the last probably 10 years where we've really seen it get this deep is that embedded IoT type systems start to look a lot like regular enterprise IT systems. So here you see something like a banking system, and you've got back-end systems and cloud-based systems and local systems and things that reach out to the consumers themselves, devices, right? It might be a card reader, an ATM device, someone's computer at home, reaching out through the network to a variety of complicated services with messages sitting on a bus and being queued and being handled by the appropriate software as it comes. And they get pretty complex. And now when we look at modern things, even something as quote unquote simple as a car has a ton of code in it, has a lot of different CPUs, a lot of different processors running specific software to do specific tasks. Many pieces of the car, not just one, can reach out and talk to different things, whether it's tire pressure sensor or Bluetooth or Wi-Fi, LIDAR, radar, etc. There's a lot of things that are talking to a wide variety of cloud services, that some of which might belong to the manufacturer and many of which don't. Maybe it's pulling weather or navigation or things like that. So it's a much more complex system. And again, we've seen the growth of cars these days, modern cars, especially, electric ADAS type cars, can easily exceed 100 million lines of code, where it used to be 100,000 lines of code. So the growth is just absolutely insane, and eventually end up with a very, very complex device that turns out sometimes there's very little tiny simple ways to get in and disrupt the entire system. In a car, for example, sometimes you can attack certain vehicles and seize control through the tire pressure sensor. And we know what happens when, little tiny attack gives access to the bigger system. It can be disastrous. So it's an important thing to think about. I wanted to give one case in this area because I think it's kind of fascinating. There was a CEO of Darktrace was talking at a conference a couple years ago about hackers exfiltrating a high roller database from a casino, and they did it through a fish tank. And it's pretty interesting because essentially there was a thermostat system, because there's a huge fish tank in the lobby, right? You need to monitor the temperature so the fish don't die. And so people reach in and check these things all from one place, and the services that maintain it can do it. Problem is that the thermometer, which probably wasn't as simple as I have here, but the thermometer system is a simplistic device, not much code on it, and not much security on it. And people think, well, what happens if someone gets in? It's not even an actuator, it's just a sensor. So, can they read the temperature of my fish tank without me knowing? Who cares? Can they change the reading? That might be more dangerous if they, can cause problems in the tank. But what happened here is that the thermometer was merely an access point that gave foothold to the network where people could get to the mainframe system and pull data from it. And the interesting thing here is the thermometer was dual use, because then they used it to exfiltrate the data as well. So in the same talk, she mentioned that there are a lot of other attacks like this against IIoT devices, whether it's CCTV cameras, air conditioning units, thermostats, etc., even vacuum robots now, and other such things. So it might happen more and more and more. In fact, we expect it to happen more and more and more. So if that doesn't keep you up at night, then I haven't done my job. Now, the interesting thing is when we talk about safety and we talk about security, obviously the big intersection of super nasty things is where things have a safety impact and a security impact. And that's where it becomes very, very dangerous. And ultimately, we also have to think about quality itself and reliability. Does the device operate properly, and does it do the thing the user wants it to do? And the reason I bring this up is that it turns out that safety and security aren't really primarily an additional effort. The things that you do that cause safety and security problems are the same things that cause reliability and quality problems in most cases. There are a few very specific things for security, like authentication, etc. But at its core, if you go read about breaches occurring right now and attacks occurring and faults occurring in various forms of recalls in medical and automotive, they call them classic programming errors. I almost hate that word because it makes it sound like they're good, but overflow, underflow, overrun, memory abuse, missing authentication or authorization, and relying on untrusted inputs. They're just, the bane of every kind of issue of every kind of software. So the downside is there's a lot of risk. The upside is that doing the right thing will help you. You're not just fixing something because you're worried about cybersecurity, but it'll make your device more safe, more reliable at the same time. So it's not as bad as you might think to try and secure your stuff. So with that, Ricardo, let's take a look at the standard itself.
Okay, great. Fantastic examples there. Anyways, I'm going to give you a glance at the standard. IEC 61508 is your basic functional safety standard. Functional safety is about incorporating into the design safety functionality that will automatically activate when issues or failures occur, also allowing the system to fail in a predictable and safe manner. An example would be your HVAC heating and air conditioning system. You have thermal sensors to detect overheating, which the electronic system will force a shutdown to prevent a fire hazard if it's overheating. IEC 61508 is not an industry-specific standard, so it can be used in many industry applications. It is heavily used for autonomous robots in manufacturing plants. And you probably noticed that slide that Arthur showed that had many types of devices, and actually that gave you a really good visual. Now, this slide shows a list of adaptations spawned to address very specific industries like automotive, rail, nuclear, and many more. Now, 61508 has two fundamental principles that must be followed. The first one is following a safety engineering lifecycle process, and it's defined based on best practices. So many highly experienced engineers from various companies authored this standard, so it contains a wealth of knowledge. The second principle is based on using a probabilistic failure approach to measure and account for the safety impact of device failure. There is something called a safety integrity level and a class level, and I'll be covering these two principles later in greater detail. And 61508 edition 2.0 is the most current version, but there have been some updates to parts of the standard, and they refer to these as technical specifications. For example, part 3 of the standard has an update or technical specification released back in 2016, which covers requirement for the reuse of pre-existing software. This pre-existing software may have been out in the field for many years, so perhaps already proven and used to be safe, or is it really? Now, the standard has 7 parts, not including part 0, and we will take a quick glance through each of these. Part 0 is a technical report for the purpose of introducing the concept of functional safety, the challenges in achieving functional safety, and a quick overview also just with descriptions and other documents on parts of the series. Now, part 1, the overall product lifecycle overview of the standard. That's what you're kind of seeing also the image on the right-hand side. Parts 2 and 3 provide requirements in determining safety integrity levels and lays out really the development lifecycle for both designing and implementing and testing hardware and software. Part 4 contains definitions and abbreviations that are used throughout the system. Parts 5 through 7 are guidelines and examples for development, and therefore very informative. Particular parts 5, which provides additional guidance and example methods on determining safety integrity levels. Now, so we'll go into a little more in depth into each of these parts. Again, a glance at this. Now, part 1 has 8 chapters, but the most important one is chapter 7. It provides the big picture and overall product safety lifecycle. You have the analysis phase, where all requirements are gathered and allocated. This includes all regulatory and customer requirements. Hazard and risk analysis is also performed, and I'll start covering this topic on the next slide because this is a very important part. Now, then you have the realization phase, which refers to the actual implementation and verification testing of the actual device, followed by the operation phase which focuses on delivery, maintenance, and disposal. I also want to touch very quickly on security. Today, as Arthur mentioned, devices are connected and smart, and they're very smart, and which makes them susceptible to attacks. You need to start addressing security just like safety has been addressed, from the very beginning of the overall life cycle. So just like you need to do a hazard risk analysis, you should also do a threat and risk assessment. Adding into your requirements, the security requirements like having secure access control, making sure you have the right privileges, you have your data protection, and have some attack detection. Anyways, these high-level security requirements need to trickle down into the realization and operation phases. Today, you have security standards like ISA 62443, which helps you address security for industrial automation. Now, to determine the level of effort required in achieving safety compliance and building your device, a hazard and risk analysis needs to be performed. You need to understand the probability of failure of your device and the consequences of the failure if it were to happen. So these metrics help determine your SIL or safety integrity level. There are several risk assessment approaches. A popular one is doing a failure mode effects and analysis using your requirements. Parts 2 and Parts 5 of the standard provide guidance and examples. The analysis results will also place your device at SIL 1 through 4. SIL 1 having the least consequences if failure occurs, and SIL 4 having the greatest consequences if failure occurs. The SIL rating determines also the expanse of functional safety requirements you'll need to fulfill. I'm going to be showing some tables that express the SIL recommended level of fulfillment in some of the upcoming slides. One other thing to touch on is having different fault tolerances in Type A and Type B devices. A Type A device are very simple devices like actuators, valves, and relays, which are primarily mechanical in nature and with very deterministic behavior if a fault occurs. Type B devices are based on complex electronics with ASICs, CPUs, microprocessors, and complex software. Now, Part 2 centers on the realization or implementation of the device. It strongly focuses on hardware and its development lifecycle. You see here shown as a block diagram. There's also a table F1 in the standard that goes into detail on what you need to do for Type A devices, and there's a table F2 also for Type B type of devices. Now, this is the realization phase decomposed into the very well-known V model. This is the ASIC development lifecycle. You can clearly see from the top left, starting with requirements, which feed the architecture design, then the behavioral modeling, then design, then synthesis, and then coding of the ASIC. And on the top right, the right-hand side, you see the verification, or you have the verification and validation phases. Again, Part 2 focuses on hardware. Part 3 of the standard focuses on the software and its development lifecycle. So now these two parts are dependent on each other, so there is a collaboration that takes place. Part 3 has its own software safety lifecycle with artifacts that need to be produced. You have requirement specification, design, development, and integration, not just with other software units, but the hardware as well. Then you have verification and validation, and operation procedures that are also required. Now, this is the software lifecycle as represented by the standard in the V model form. Know that this is the recommended software development process. It's not to be taken as a software development methodology. The standard does not care if you use the waterfall approach or an agile approach or some hybrid approach. Now, Part 3, I'm going to be going to show you some of the software safety techniques that are recommended or highly recommended by the standard based on the SIL level. So as you can see here in this table, we have at the very top, you have your technique, and then you have different recommended or highly recommended SIL requirements that you need to satisfy. Now, as you see here, Table 1 states that in the requirement specification artifact, you need to include forward and backwards traceability. A bidirectional traceability matrix is really what you'll want to deliver. It helps expose gaps between and from requirements to design, code, and testing. Now, this bottom table is an example of requirements traceability in JAMA. So you have ALM tools, such as JAMA and Polarian and so forth, that capture all of these requirements, and you'll be able to then create that traceability matrix. Now, this table shows how Parasoft extends the traceability down to the test cases, the code, and code reviews. It really satisfies or completes that full traceability that is required. Now, Part 3, here again, regarding the section in software design and development, you have requirements for strongly typed programming, defensive programming, the use of design and coding standards, and more. I recommend that you adopt one of the several coding standards like MISRA, AUTOSAR for C++, and start detecting safety issues. For security vulnerabilities, I recommend CERT and UL 2900. Another key requirement captured in table A3, row 4A there, is used for certification. Make sure you use certified tools. You want to make sure that any tool you use to develop your safety system has been certified. This means that they have been tested and won't introduce flaws or issues into your design, code, or testing. Parasoft is TÜV certified for use on safety critical applications. Now, regarding the section on verification and validation for static analysis, these two tables capture a list of requirements that your static analysis solution should perform, such as data and control flow analysis, symbolic execution, no use of dynamic variables and objects, limited use of pointers, and actually quite a lot more. Now, Parasoft easily fulfills these requirements by integrating static analysis into your developer's IDE and many other testing methods, which I'm actually going to cover next. Besides static analysis, we should be testing, first testing methods that you need to use, such as dynamic analysis. This is when you start testing through execution, like unit testing, integration, and system testing. And all of the test cases that you create should be reused for regression testing and revalidating the complete system. Again, Parasoft automates all of these testing methods for you. Now, on top of that, we have integrations with a comprehensive set of compilers, debuggers, and embedded target development environments. So very powerful solution that we have. I just want to give you another visual on Parasoft, the tool itself, see how it looks within the Eclipse IDE. Again, it's a unified static and dynamic analysis testing solution. On the bottom right, I know it's a little bit hard to see there, but there's a window of configuration on how you can automatically generate test cases. We automatically generate smart test cases, which is actually a huge productivity gain for your organization. We have here table B2. It shows some of the types of auto-generated test cases that we perform, boundary value, error guessing, and many other types. But also, it's important to understand or know, when are you done testing? Well, we also perform structural code coverage of statement, branch, MCDC, call or entry, and other types. You also see the green highlighted code indicating that it has been executed and tested. Now, here's just a quick little report based on our analytics dashboard, showing you the code coverage achieved from various testing methods, like unit testing, manual, and more. So you can actually combine all of these tests, testing together, and capture your complete coverage. This is just another more comprehensive look at several dashboards capturing the status and progress towards compliance to the standard. Now, part 4 of the standard contains all of the definitions and abbreviations used, so very easy to read. Part 5 contains supporting documentation and examples for determining your safety integrity level and the risk class. A class 1 device failure will have a catastrophic consequence. A class 4 device failure will have a negligible consequence. You similarly see this kind of classification used in the medical industry. Now, part 6 has a collection of annex sections which give additional guidance and examples in support of the realization phase, so it supports parts 2 and 3. Similarly, part 7 has a collection of annex sections providing an overview of techniques and measures for all of the parts in the standard. Now, this is the Parasoft V model to give you a high-level view of the solutions that we offer. for each of the phases in the development life cycle. On the left-hand side, we support your requirements traceability needs. On the right-hand side of the V model, we have a plethora of solutions in the verification validation phases. Again, be aware that Parasoft solutions have been TÜV certified for IEC 61508 in use on safety-critical devices. Okay, I hope the glance of the IEC 61508 standard was very educational. I really highly recommend that you visit our website. We have tons of great informative content. I've included these QR codes where the first one will take you to a demo video of Parasoft C, C++ test, so you can actually see it in action. You'll see there a presentation, see how the tool works. It's fantastic. We also actually have now a tutorial option, meaning that you can take a tour of the product, the C, C++ test online. So look for that option. And if you're going to be at the Aerospace Tech Week in Toulouse, France next week, please come on by our booth. We would actually love to meet you. All right, I'm going to go ahead and open it up for Q&A.
Yes, Ricardo, I did want to mention one thing about that tutorial for those who aren't familiar with it. This isn't just like watching a demo, right? You actually get to interact with the product a little bit and choose your own paths and the things that are important to you. So it's a really cool way for you to check out what we have without having to install and execute and do all that stuff. You can find out really, really quickly what the software does. So I encourage you, if you haven't ever tried one, to check it out. It's pretty cool.
Mm-hmm.
So on the question side, we have one about certification. So who certifies products to be IEC 61508 compliant?
That's a good question. It has to be a third-party company. The most well-known to me are Exida and Baihan, which have they've been actually given the authority by the ANSI Standards Organization here in the U.S. So you have the American National Standards Institute, and for the U.S. And then for Europe, you have the European standards organizations like CEN, the European Committee for Standardizations, or CENELEC, European Committee for Technical Standardization. I'm trying to remember all these acronyms. And I think there's one other one as well. But they give a company the authority based on, if they learn and take classes and get certified to actually be able to do that. So that's how they get certification.
Yeah, I would add to that Etsy, but not the one where you buy hand goods. The European Telecom Standards Institute, right?
Yeah, that's it. That's the one I was forgetting.
Yeah. Okay. Another question: is it possible to automate testing as part of a build process with Parasoft and Azure DevOps?
Oh yes, absolutely. So really, many, if not all, of our customers and prospects are looking for automation and test solutions that work within their CI pipeline. There's a lot of productivity gains there in just cost and time to market. So we've been making sure that Parasoft, our development tools, have integrations with Azure, DevOps, GitHub, Jenkins, GitLab, and many other tools that are part of that CI/CD ecosystem.
Great. And another question: is it possible to try out these tools? If so, who do I reach out to?
Yeah, absolutely. It's possible. There's several ways. You can contact Parasoft via email and send an email to info@parasoft.com, or you can visit our website, www.parasoft.com, and you will find several buttons. There's a Get Started button on our main page. This will take you to another page where you can actually have multiple decisions there, such as talk to us, request a custom demo, and again, exactly what we talked about, the take a simulated tour of the product. And we're building multiple tours of our products as time goes. Anyways, I highly recommend that you visit our website. Tons of content there that I think you're going to find very educational and interesting.
Yeah, and you can even talk to our chat bot there. He won't bite. He's completely safe because he doesn't have any physical manifestation.
Yeah,
Well,
Is it
great.
cool?
That's it. We thank everyone for your attendance today. If you've got further questions, please let us know. As I mentioned, you'll get a link telling you how to get a copy of the slides or to watch the presentation. And again, feel free to share it with your friends. Let them check it out as well. If you have specific information you'd like to know more about, perhaps other standards that we haven't discussed yet, or areas where you'd like to dive deeper, like more about coverage, more about unit testing, or more about the SIL, please let us know and we'll try and get it into our webinar queue. And with that, thanks everyone, and we hope you have a great day.
Thank you, everybody.